Hello. This week I want to talk about hardware, computer hardware. So we all buying new computers, new smartphones every time. And we, dealing with processors and gigabyte of RAM and so on. But most of us have very little understanding of what that actually means, what it's good for, and what the actual value is, and also what your demand is. And in this lecture, I want to talk about how you can estimate the demand of your numerical model from the computer hardware side. How to estimate that, what kind of memory demands you can have, what does it mean? I used the term a lot in the last couple of weeks, computational costs, and how you can estimate those kind of costs. So why are we worrying about performances at all? So we want to simulate the complex world outside. And this usually requires enormous computational resources. And there is, on the other hand, a rapid development in computational resources in the last couple of years or decades even. And what we can do now is have those technical benefits be used for our purposes. So for our for improving the quality, the demands of our numerical models and what we are able to describe by our numerical models. So we are talking in some sense then about optimization technologies. So what can we do is about parallel processing, right? So when you have a modern computer, it has multiple computer cores, and how you can set those multiple cores and processors to the benefit of your simulation. All right, and we'll talk about cost and cost efficiency. So of course, the more money you spend, the better PC you normally get. But if we're talking about supercomputers, it gets very expensive very quickly. So how can you use multiprocessor hardware in terms of clusters or so of off-the-shelf processors to use that as your tools for improving or being able to conduct more complex numerical simulations? So what is important for us in numerical modeling, of course, is a processor, which is a bottleneck for the speed of our simulation. We need to talk about RAM, so our processing random access memory, because that's where we store our information. We'll need to talk about hard disk drive, because that's where we have the permanent storage for data. Of course, also power supply and cooling are relevant. We're talking about high performance. You might want to consider a GPU, so for a video card, for not just for visualization, but also for computation. And if you're talking about clusters, network like Ethernet or InfiniBand, are other factors, which I will not have the focus on in this lecture. So the power supply is very simple. It alternates or converts the AC to the DC, and it simply needs to be sufficient to power all the ingredients. So if you reassemble a computer yourself, make sure that your power supply is sufficient to provide the power to all the different pieces you're putting in there. If you do not make this sufficiently, or if your power supply is very close to its limits, it's often the first part to get broken. Cooling, you usually do not have to worry about. It's based on fans. Nowadays, several components have their own fans for example, GPU or power supply. But yeah, so those are your basic things you usually do not worry about so much, besides if you reassemble the computer yourself. So the central processor unit, so the CPU, that's we consider the computer's brain. That's where the work is done, where the calculations are performed, usually if you're not using GPU, so the graphical part. Nowadays, this CPU consists of multiple cores. Pretty much like 4 cores is standard nowadays, pretty much. You can have up to 6 or 8 cores, actually. The idea with those cores is that each core can process information. As more cores you have, as more information can be processed in parallel. Right, so like if you have a computer and you're using it regularly with, like, I don't know, your operating system, let's say Windows, and you have some internet browser and you maybe some Word document. So it could be that those programs are operated on different cores, so they all can run smoothly separately. Then there is another thing which is called hyperthreading, which says, okay, your computer actually as a hardware has 4 cores, but the operating system, or even the system below that on a hardware level, is simulating that as 8 cores. So it usually doubles the numbers of cores there are. But however, you still have only 4 cores physically. But the idea is that if you're a regular user, as I said, just operating system with a bit of internet browsing and then Word documenting, your program is not requiring your core to be under full load all the time. So there's idle time where the core has nothing to do. And so what the computer very intelligently does is when it's simulating 8 cores, but there are only 4 cores, it always shifting the tasks on the virtual cores in the idle times of the physically existing cores. However, if you do a well parallelized simulation, this is rather disadvantageous, right? Because then you don't have any idle times. Your computer is under full load all the time. But if you make it 8 cores, so 8 threads, as we will learn in a second, but you only have 4 cores, this is difficult because the computer has no time from the 4 virtual cores to merge the load from those 4 virtual cores into the load of the 4 physical cores, because the 4 physical cores are already busy all the time, right? So usually you do not open more threads than there are physical cores, right? At least would be my recommendation. As you probably know, the CPU speed is expressed in cycles. So nowadays we have gigahertz, means as more cycles it has, the better, the higher the speed of the calculation. Now we have the persistent data storage, so your hard drive, very much, and the values to express it are 2 values that are relevant for you. It's the capacity, so how much data can be stored, that's gigabyte or terabyte. Nowadays usually a couple terabytes, and the speed of the reading and writing, right? So that's measured in revolutions per minute. And the classical one up to a couple of years ago has been the HDD, which is a magnetic storage with moving parts. So you have this rotating disk. This has been, it's still available, especially as external storage or in desktop PCs, because nowadays it can be produced rather cheaply. However, in modern laptops and so on, you will usually get SSD, so solid state drives. It's a different kind of storing data. It's not moving parts anymore. It's integrated circuits. So it's way more robust to be transported. So that's why we usually use SSDs in computers or external hard drives, which you want to take with you and carry around. It also has much faster reading and writing operations, but because it's rather new technology, it's also more expensive. But well, if you have the money to spare, then an SSD is always recommended from my side, at least, because it reads and writes the data faster, which can be beneficial if you need to access your SSD. So you can imagine you're running a simulation, and for example, you want to have like doing an I don't know, a solid transport modeling about 100 days, and you want to save the snapshot after every day. And it's too large to have all that one stored in your RAM. So you want to write it to your SSD or to your hard drive, to be more general. At that point, this reading and writing speed matters because your calculation stops, so your CPU has nothing to do, or not much to do, because now it's just saving the amount of data, which can be huge, into a file or multiple files on your hard drive. And then as quicker your hard drive is, as quicker this process is, and then you can continue calculating. Right? So this is something where your reading and writing speed comes into play. So for example, what you can do is you use an SSD for those kind of operations, and when your simulation is done, or at the end of the day, you're copying the data that you've generated and that is saved on your SSD towards an HDD, which is cheaper and where you do not matter about the reading and writing time, because it's just there for storage and you're not actively working with it, you're not actively accessing it, right? So we use the term the RAM, the random access memory. This is the place where your computer stores all the data that you are currently needing, accessing, right? So if you generating your mesh and you're parameterizing it and you're assigning the parameters for the hydraulic head, for the permeability, for the porosity, all this information is stored in the RAM. Okay, so as larger your mesh is, as more points your computer has to save to the RAM. And you're running into problems if you are requesting more memory than you have as an available RAM. Because then your computer will store your data, although it needs to be accessed regularly, not in the RAM because the RAM is full, so it will be stored on the hard drive. And that is comparably slow. And also you will notice that a lot of software will tend to crash if you have a so-called memory overflow. So if you're requiring more memory than you already actually have available, right? And your computer will just become terribly slow. So this is why memory management is a crucial part of simulation. Before starting your simulation, you have to imagine, okay, how much memory do I have available? How large my arrays will be? Because this will also, from a hardware side, right, limit your mesh size. And we will do some exercises on this in a second. We also have the main board. If the CPU was brain of the PC, then the main board is the heart of the PC, because this is where everything else gets connected to. So, you know, it has the slots for the CPUs, for the RAMs, for the fan, for the power supply. So this is where everything becomes connected to each other. And for example, every mainboard has a limited amount of slots, if, for example, for your memory, or for your numbers of GPU cards that can be connected, also for the communication, and so on. So, you know, it need to be matched to what else you have as a demand on CPU, RAM, GPU, network, and so on, right? So it doesn't do any work by itself besides connecting all the other parts. But as NAS, as this part, it determines also the communication between the different components. So it's worth not just getting something that is matching to the other parts, but also something that is, you know, sufficiently fast for whatever your task will be. Now, this will be the next couple slides, a bit of a theoretical excursion towards informatics and mathematics. But if you want to assess the speed and the memory demand of your computer, it is worth, you know, digging into a bit. And well, you can consider it also part of general knowledge these days. So I want to first of all introduce you to a couple terms, an integer and a float. An integer value is just simply a whole number, like 1, 2, 3, or -1, -2, -3, -500, whatever. There is no decimal place. Okay, it's not 1.0, it's just 1. Because the floating point value would have been that decimal point. So -3.0, that is the float. You know, we in common language do not separate between 3 and 3.0, but the computer does, right? So an integer as a classical value for for example, a loop parameter. So if you want to go through an array and you go 1, 2, 3, 4, 5, talking about discrete points in your matrix, then you have an integer. If you're talking about physical quantities, temperature, concentration, hydraulic conductivity, and so on, then we are at a float, because this will be 3.0005 or things like this. And if we have an integer or a float, makes a crucial difference if we're talking about numerical calculations and the storage of those values in the memory. Because, as you probably know, a computer is calculating in O's and zeros and ones, right? So if we have a number, it is stored in bit, or let's say in 32 bits. And of those, if we have an integer, of these 32 bits, 1 bit is used for the sign, which gives us a plus or minus, depending on 0 and 1. And we have 31 bits for the value. And this then, because as I said, storing values in zeros and ones is a bit different. I don't want to get into that one, but gives us a value range. With 31 bits, we can store 2 to the power 31, or the minus 2 to the power 31, as a lower limit, and the same one, just minus 1, as an upper limit. And if you have, so for calculations, we don't usually calculate in bits, but in bytes. And the definition is that 1 byte are 8 bits, so 32 bits are 4 bytes, right? And then we come to these megabytes, terabytes, and so on, the colloquial values from your storage of data storage. For a float, this looks a bit different because it is stored in a different way. We have 1 bit for the sign, so we still have 32 bits to fill, right? But we have 1 bit for the sign. This is similar to the integer. But then it's more efficiently to be stored if we have 8 bits for the exponent and 23 bits for what you call the mantissa, so the value prior to your exponent. And so the maximum value, we can still calculate what can be saved, is 3.4 times 10 to the power 38, which is larger than what we can do with integers. But if we just have 8 bits for the exponent and 23 bits for the mantissa, we cannot, save, of course, every decimal position after the 0.4, because you only have roughly 6 to 7 decimal digits. That means if we're going to the upper limit, we can store something like 4.515323 times 10 to the 35. But I cannot specify what comes after the 3. Okay, because I have only the memory to store 6 to 7 digits. Similar is if you go very small, right? So this is very, very small, but my accuracy kind of stops here because I have not the space to storage any further. Which means you're not storing really the whole value, right? You're just storing a couple of decimal digits, and all the other things is, dropped, and it just remains in the exponent. So you can notice here that this limits your accuracy if you come to multiplication or things like this, right? Or adding maybe very different values of scale, right? If I would add those 2 ones here, this would be a result. It wouldn't change because whatever comes here, because it's so much smaller, those digits would not be stored here. So that would be like adding 0. Like I wouldn't have the space to store this kind of change. So if you want to calculate your computational costs, so for example, in terms of memory, and you want to access your memory demand, we will do a simple example here. Assume a regular grid. So we don't want to save, as you said, told you in the very beginning of these lecture series, in an unstructured grid, you have not just to save the node position, but also who's the nearest neighbor and so on. I don't want to worry about that. I assume a regular grid. so I don't need to have these additional amount of memory demand. But I want to solve groundwater flow equations, so I need to store at least two parameters, transmissivity and storativity, and I need to solve for one variable, so the hydraulic head. So the minimum, which is not even sufficient, but for the calculation we just keep it to 3. This would be the 3 areas I need to save. We will consider a regular grid size, like 200 times 100 points, nothing too fancy, but it gives us 20,000 entries. Now we have 3 variables, or 3 values to store: transmissivity, storativity, hydraulic head. So we multiply the 20,000 times 3 gives us 63,000. Now we have all with these 3 parameters or variables having a 32-bit float associated with it. Doesn't matter if it's integer or float, but it is a float. So let's keep it like this. We have the 60,000 entries. Each entry is 32 bits long, which results in these 19.2 million bits. Now I can divide it by 8 to come up to the bytes, which results in 2.4 million bytes, which is nothing else than 2.4 megabyte. Simple, right? But note, now this is just the memory demand you are seeing. Remember that if you use any kind of time stepping, you will not only need to save the hydraulic head of this time step, but also of the previous time step. So that would already be twice. You're not considering here all the memory demand you have for setting up the linear system of equation. You have an iterative procedure, so there are different intermediate steps where you need storage for. So your actually memory demand will be significantly larger than those 2.4 megabytes. Those 2.4 megabytes would be if you would really, just output those kind of values to, your hard disk. Well, okay, so this what I just said is written here. One interesting point is that we have the 32-bit, what we call nowadays single precision. If you buy a modern PC, you will get also for your operating system, or say, well, tell you it's a 64-bit, pardon. Not 62, but 64-bit. There's a mistake here. And this is what we call double precision. So if you have a 62-bit operating system, or so, it just means it is operating on a 64-bit regularly, which would increase your precision to then having 16 relevant decimal digits, right? Because you're not increasing so much on the exponent, but on the mantissa. Yeah, you have sufficient more parameters to store there. So it should be 64-bit, not 62. So computational costs is, if you really go into computational science, you will see it's not that trivial, right? There are also formulas to estimate it, different definitions, rules of estimation, and you can also, there's a term called computational complexity. So we're not doing computer science here, so I don't want to get too much deep into here. For me, computational costs, as you should worry about them as a modeling in groundwater modeling, are execution time per time step of my simulation and the memory demands. Right, so costs usually increase with my problem or input size. Right, if I have a larger grid, I have to store more information into my into my RAM. I have a larger matrix to solve more more equations, more linear, a larger linear system of equations. So there are more calculations required, increasing my execution time per computed time step. And then, as you know, talking about stability and accuracy, if I have more grid points, I have smaller grid distance, means I might be required to have a smaller time step, which means I need even more calculations because I have to solve the linear system of equation more often. Right, so this is what I'm summarizing out of these terms, computational costs. And this mainly addressed hardware side by the CPU and the RAM. So when you want to assess your computer's performance, depending on your level of application, so if you're a programmer yourself, You have way more opportunities than if you're just a user. But there are also a couple of things you can do as a user to improve the performance of your computer. So general rule is, as a programmer, integer operations are easier than floating point arithmetic, so the computer can do those ones more quickly. Point calculations, so multiplication and division, are more complex than addition or subtraction. You can, in general, it's a good way to reduce the number of calculations necessary. So, for example, you have an often used combination of variables, something like hydraulic conductivity multiplied by the size of the time step divided by storativity and the distance of your grid points. All right, regular one. It's more efficient to calculate the ones, store it as a variable in your memory, because memory is usually cheap. And so instead of calculating these, then it's already 3 calculations, right? It's 2 times the multiplication and 1 time a division. Right? Instead doing those 3 steps every time, your computer would just access the variable in the memory and use this one. So you can save time with those kind of tricks. But this is mainly done on a programming level. As a user, you can do something like reducing the output, right? So generating a graphical output, so showing you the pressure distribution at each time step, slows down your simulation, because what your computer will do is it will do the calculation will stop, it will execute the necessary commands. So the CPU will talk to your operating system, to your main board, run the commands to trust the graphical processing unit. The graphical processing unit will generate the output, talk to your screen. There's a lot of things going below. And actually you just want to have your computer run. So if you reduce the graphical output, you go much faster than if you have a graphical output every time. Also, saving to the hard drive takes you time, because the same thing happens. Your CPU stops with the calculation, talks to the main board, talks to the hard drive, the commands are executed on operating system level, stuff like this. It takes time. And of course, sometimes it's necessary, no question, but make it reasonable, right? Not putting the output a million times the same results for different time steps, but say, okay, might have a time step of an hour, but I'm actually just carrying how it looks like at the end of the day. So you're just saving every 25th time step. You can also in general reduce unnecessary computational load. It goes as simple as that. Close unused programs and windows. Do not merge things on the side, because if you have a well-performed or well-programmed computer program for the modeling, it will keep your CPU under full load the whole time. So there's this huge term, supercomputing, high-performance computing, and most of the people, if you say some of these, people will think of these high, very, very expensive HPC centers around the world and who has the fastest and so on. You measure those kind of operations, or the performance of those computer centers, in floating point operations per second, flops. So this, what you see is, because that's what you want to use those computers for, right? We're using those for very complex calculations in every kind of subject. But we usually do floating points operations, so measuring the performance of those computer clusters, how quickly, how many of those operations it can be done in a second is a crucial parameter. What if we just take a step away? Whatever any HPC center is, it's a network of extremely powerful PCs where someone paid a lot of money for. There are also applications for HPCs in geosciences, right? This is absolutely normal. A lot of geoscientific simulations are run on those kind of computer clusters. that you yourself, if you're not going into research or conduct numerical simulations on those kinds of HPC, might be rather unusual. But we can use those techniques that are applied in those computer centers, although at home in small scale networks or even within our own PC, or single PC. Right? But that means we need to make sure for us what are actually our computation requirements. What do we need on memory, on CPU speed to conduct our simulation? And the basic thing what I want to do is, and what those kind of supercomputers do, is parallel programming, right? So the idea of these centers is not simply like having one super fast PC, because as I said, it's a network of a bunch of very, very fast CPU computers. So by not using one fast PC, but using 10, hundreds, thousands of very fast PCs, I'm able to calculate efficiently or in a reasonable time span very complex problems. And the world around us is parallel in nature, right? It's not serial. It's not like I'm moving my hand and then someone else is moving the hand, but we're all moving our hands together at the same time, simultaneously, right? So the laws of physics apply at every time and in every point in space. And if you think in terms of this fine differences approximation, that what kind of physical quantity we have in the future, so the near future, consider temperature, that depends on the present state. What is my temperature right now? On the immediate past, what was my temperature a second ago, a minute ago? And the neighborhood, so how's the temperature on the left? How's the temperature on the right? So those things, if you're really thinking in terms of fine differences discretization, right? This is what my physics depend on in the near future. So when I want to do parallel programming, so running different parts of my code in parallel, I need to ask, okay, what can actually be efficiently parallelized? So what is independent of each other? What can be calculated simultaneously? And what depends on each other? So what do I need to know before I can do another simulation, another calculation step? So the idea of a serial programming, and that's what the most common way actually is to think about those things, is a serial style. So I have one computer, one processor, and this is doing one step after another, one calculation after another. All right, so there's a logical sequence which the program goes through, and if it's at the end, it just stops, or it starts at the beginning, depending on how it was programmed. But there's just one operation at a time. The idea of a parallel computing is I do pretty much the same, but I'm not using one processor, but I'm using multiple processors. And now my only question is, how can I divide my problem, my big problem, into the required number of processors? All right, so first of all, I've used one CPU. Now I want to use 4 CPUs. So I want to have a load balance, so each core equally busy, right? So that is down here. I have to think, okay, how do I divide my problem into 4 pieces, which are all equally large, and so that I keep all 4 cores that I have available busy the whole time, right? And you can do this by a function decomposition. I can say, well, this processor 1 will calculate my flow. The second will calculate my temperature. The third one will calculate my solute transport, and I have no idea whatever the fourth one will do. That would be a functional decomposition. The question is, for example, if those one could be computed actually in parallel, because temperature and solute transport would need to know the flow velocity. So that means I would have need to calculate first my flow, then I can compute the other 2. So more common there maybe is a data decomposition, which means I have my domain, which I split into 4 pieces, and each of my 4 cores does all the functions. So it will calculate flow, it will calculate temperature, it will calculate solid transport, but just on a part of the geometry and not on the whole geometry, which still means I'm having 4 operations in parallel, so I only need a quarter of time. If I want to run things in parallel, there are 2 main ideas to be separated. The one is the shared memory idea, which means all my computer cores have access to the same RAM, which means in the end I have one large powerful PC, because it means I have a CPU unit with a big bunch of cores, 64, 128 cores, whatever there is on supercomputing, but they're all accessing the same amount of RAM. Not just the same amount of RAM, pardon, but exactly really the same RAM. In the distributed memory, this is what we have in computer networks, means each core has access to RAM, but not all cores have access to the same RAM. That means I need to communicate, because it could be that processor 2 needs some information of some points which are computed by CPU 1, right? Because, well, we want to have a consistent formulation, so that means there may not be a gap between the different domains if you think in a geometrical splitting, parallelization of your code. So at least at the borders of each domain, they need to communicate, they need to exchange their grid points, the values of their grid points. So there's communication required in a distributed memory. I do not have that in a shared memory, but of course, if you think in scaling a distributed memory, it's, you know, it's just regular PCs. I can add more and more computers by the network without, well, can be done rather cheaply, than adding more and more cores to one similar PC. So getting a bit more into detail, the shared memory means all cores have all information. That makes my parallelization rather simple. And nowadays, depending on what kind of parallelization library you use, well, as a programmer. So if you buy a parallelized program, as most programs are, shared memory is the most common technique, because it is very simple to implement, right? It will do the load balancing automatically. So let's say, for example, you have a solute that is coming from left to right through your domain, which means at the beginning, your left domain has a lot of calculations to be done because there's tracer transport. On the right, there's nothing done, which means the cores that are responsible for the left part of your code have a much more higher load than the cores that are responsible for your right code. And load balancing means like that the right core, that the core says who's required to calculate the domain on the right says, well, I'm already done, so it will automatically take over a bit of the load from the cores that are under heavy load and have to do all the things on the left side of the domain. So all this is done automatically and you don't have to worry about it. That makes it very, very nice, to say so, for programmers and for users. And this is where these word thread come in. We had this very much at the beginning as we used the term hyperthreading. So if you have 4 cores, so I don't know, Intel E7, 4-core, whatever, means you have 4 cores, so you would open up 4 threads, right? I recommend not to open up more threads than there are physically cores. So the threads is what you can think of in terms of well, order pipeline, right? So it gives you what can be done in parallel. But for example, if you know, well, I'm running the simulation on this computer, but on the other side, I also have to do, I don't know, check my emails, write a report, whatever. So you might want to know, okay, I will put 3 cores. You will use 3 cores for your numerical simulation. You will have 1 core spared for whatever else to do. You know, then you have 4 cores, but you would just open up 3 threads for your simulation. It can be that your software allows you to specify the number of threads. Some software will just assume that you want to have your simulation run as quickly as possible, so it will automatically check check how many threads there are, how many physical cores you actually have, and we'll just open up as many threads as there are physical cores. This is a bit, you will figure it out depending on the software you're using. You can either specify the number of threads or not, but never set the number of threads to more than what you have as physical cores. In a distributed memory, it's also often called message passing. Right? We already said we need to communicate between the different components because the different subdomains might need information from the other ones. And this usually, takes time. Communicating always takes time. The different techniques, I don't want to go into detail because most of you will not program this just themselves. But it can be less efficient if there is not a good load balance, because faster threads need to wait for slower threads because prior to continuing the calculations, they need some information from the slower threads. Things like this can happen. But there is a very much benefit to those kind of distributed memories. And this is the scalability. So you can set up a system for distributed memory and you can still run it on a single PC. So you're doing maybe unnecessary communication because, well, the whole CPUs had access to the same memory, but it doesn't matter. You can run the same problem on a single PC as you can run on a huge computer cluster. You can even run it on a high performance computing center. So one of these big expensive things, we talked about it as an entry to this topic. So this scalability is a big benefit of distributed memory, right? For you as a single user, if you are running on a single PC, it's not really required. It might even be slightly bit slower than a shared memory approach. For the programmer, it's much more effort, at least from my point of view. But it has this benefit of scalability. And for any problem in simulation, you will run to limits, right? Either the next step of adding more cores to the CPU, it's not even possible, or it's just incredibly expensive, or also kind of memory that you can add to a single computer is limited. So at some point you will not have any other possibility than use distributed memory parallelization. It is sad. It then really goes towards high demanding computations. But there are benefits in distributed memory. It just means it's maybe a bit overload for many of simulations you will conduct on a regular basis if you're like in an engineering office or a federal office. But still the technique is there and it has its use cases and it has its strong benefits. Just very short notice about GPU. It might come across if you really talk about high performance computing, because it has gained a lot of attention lately, also in terms of, for example, on Bitcoin mining and stuff like this. So GPUs are originally designed to manipulate huge amount of data rapidly for visual output, right? So really think here in video gaming industry, in all that kind of things. You want to have as realistic optical presentation. So you need a huge computational power that addresses your huge screens, all at the same time, all the different pixels in the same time. This is what GPUs were optimized for. And although GPU consists out of cores, and if you compare directly a GPU core to a CPU core, the GPU will be much slower. But there are hundreds, thousands of GPU cores on a single GPU. And this is the benefits, right? So there's a GPU, just this parallelization by its heart, that's what it's good for. It's intrinsically the benefit of a GPU. It has its own memory, right? Similar to RAM to CPU. It has its graphics memory. If you're buying high-end graphic cards, these will be given on the label. So this is why you have GPUs nowadays in high performance computing. GPUs have the downside that they fail if you have an unbalanced load, right? So as I said, each core is comparatively slow to a CPU core. So if one core has much more load than other cores, all other cores wait till this really slow core is done with its calculation. And that is where GPU is not good at, right? At load balancing. So you need to have your code. If you can balance your code equally on each core, a GPU, is state of the art to use, right? That's kind of branch prediction. So as a programmer, if you have a lot of if loops in there, a GPU is better. But for you as a node programmer, it's mainly to know that there is something like this, and maybe you will buy software in the future which is running on GPUs, and they do this efficiently on the downside. Also important to know is a GPU is a tool to communicate or to do the calculations, better to say, but it still needs to communicate with the other parts of the computer, and this is still done by a CPU. But then you can use some kind of cheaper or slower CPU, because the heavy load, the computation, is done on the GPU, right? But this is just good to know. It definitely is a reality in a lot of applications, not so much just yet in groundwater modeling, but it might be in the future. Whoever knows what the future holds for us. So coming to an end, I hope you understood that hardware management is a crucial part of programming. Right? Not just of programming about any kind of numerical modeling. Right? I just highlighted the three components: processors, RAM, data storage, as the most crucial ones. And you should estimate your hardware demands before, right? It comes already on conceptual stage. It comes so much into it. What can you have as a grid resolution? How many data points can you have? How much or how large you can choose your domain based on the numerical resolution you might need to require, about how much computational costs in terms of runtime you have depending on your temporal resolution. When do you need a graphical output? When do you don't need a graphical output? When do you need to save something to hard drive? All those kind of things you can optimize for your calculation, right? And it is a huge word, high performance computing, but a lot of software you will buy will make use of parallelization techniques, being it either shared or distributed memory. So you should know the difference by now. So those techniques are available in software packages you can use just right now. But you should, as a programmer or as a modeler, you should know what they do under the hood, right? So that when error messages pop up or things like this, you can, you have an idea about what you've done wrong if there comes up memory overflow or things like this. Thank you very much.